Standard geodynamic models categorize tectonic shifts as localized events driven by chaotic mantle convection. In this view, the movement of plates is the result of heat-driven turbulence deep within the Earth. This reliance on chaotic convection creates a significant gap in predictive power. It leaves researchers unable to anticipate major macroseismic events with any degree of mechanical precision. The Afar OS model offers a different framework, treating the Earth's crust as a managed, closed-loop technical system. This system maintains planetary equilibrium by distributing internal thermodynamic and kinematic pressure across a planetary geometry of 19 primary energy nodes. Modeling the crust as a regulated technical interface allows us to identify earthquakes as the quantifiable mechanical outputs of these specific pressure points. The core mechanical problem is simple. The Earth's mantle generates intense internal pressure that must be balanced by the rigid crust above it. To manage this load, Afar OS utilizes a specific, mathematically optimized geographic geometry. The pressure is vented and balanced through exactly 19 hotspots. Mapping the distribution of these 19 geometric nodes across the tectonic plates reveals the structural framework of this planetary network. These static nodes are governed by a synchronized temporal code. This code dictates exactly when each node is scheduled to release its accumulated energy. By reconstructing the spatial mechanics and the temporal triggers of this 19-node model, we can verify the physical basis for the 2026 to 2027 forecasts. Precise forecasting requires the intersection of both datasets. Mapping a geographic location is only useful if the planetary timecode for that location is known. Each node in the 19-point network performs a distinct mechanical task within the overall system. Node 1, located at the Hawaii hotspot, functions as the central mechanical driver and the primary time indicator for the entire Pacific plate. Changes in activity at Node 1 provide a direct metric for the movement of the largest tectonic plate on the planet. Node 2 in Iceland serves an entirely different function. It acts as a thermal link point within the global network. Iceland's mechanical role is to connect and balance the thermal pressure distributed along the mid-Atlantic ridge. These oceanic hotspots act as kinetic engines, physically pushing the boundaries of tectonic plates to maintain the planet's structural balance. While oceanic nodes drive kinetic movement, continental nodes function as extreme pressure relief valves and energy reservoirs. Node 3, Yellowstone, is the largest continental energy storage unit in the system, a supervolcano capable of holding massive amounts of thermodynamic stress. Yellowstone's deep storage function contrasts with Node 8 in the Indian Ocean, which provides constant pressure release through basaltic flows. Node 4, located in the Afar region, is the mechanical engine currently driving the separation of the Arabian Plate. The Afar node serves as the specific trigger for the rifting process that is expanding the Red Sea. This diverse array of 19 nodes creates a balanced global network optimized for planetary pressure management. Geography defines the locations of the nodes, but a celestial mechanism determines when those nodes will activate. The 18.6-year lunar nodal cycle is the external engine driving the system's timecode. Over this 18.6-year span, the moon's orbital tilt gradually shifts its gravitational force on the 19 identified nodes. This pulse of gravitational energy acts as a planetary metronome, timing the activation of the Afar OS nodes. This temporal code is a predictable wave of gravitational force that targets the most vulnerable points in the Earth's crust. Crustal tidal stress physically warps the rigid rock. The 19-year lunar wave induces mechanical friction and stress as it ripples through the crust. At the same time, internal mantle pressure continues to accumulate steadily beneath the 19 hotspots. When peak internal pressure at a node coincides with the peak of the 19-year external tidal stress, the system reaches a breaking point. This external gravitational stress acts as a mechanical trigger switch, forcing the release of energy through volcanic or seismic events. Catastrophic events occur when this binary alignment of internal pressure and orbital timing is achieved. Applying this 19-year ruler to current data places us within an active predictive window from 2024 through 2027. Researchers use geographic data isolation to determine which specific nodes are currently primed for a release. This process identifies Node 4, the Afar region and the Arabian Shield, as the model's most critical immediate target. The model predicts the continued expansion of continental faults and increased seismic activity throughout the southern Red Sea. The Arabian Plate is currently under intense mechanical strain as it synchronizes with this 19-year gravitational pulse. The predictive window for the Afar node is currently open, and the region is reacting as the 19-year tidal stress framework dictates. Beyond the active Afar window, the model has isolated another primary target, Node 3, at Yellowstone. This map of the Yellowstone region incorporates current hydrothermal data, showing a marked increase in seismic activity across the caldera. This data indicates that Yellowstone is currently within its peak 19-year stress accumulation window. The final target involves a forecast for submarine activity near Easter Island, which will alter the pressure balance of the Nazca Plate. These geographically diverse locations are all linked by the same 19-year temporal pulse acting on the Caliphate OS nodes. The Caliphate OS model synthesizes the 19 geographic nodes with the 18.6-year planetary pulse. Decoding these planetary timecodes enables proactive modeling, which uses current load data to anticipate failures before they occur. This provides a method for proactive geophysics, moving away from reactive logging toward a predictive engineering model. This predictive capability is absolutely essential for monitoring and protecting civil energy infrastructure situated near these active nodes. Treating the Earth as a regulated, mathematically predictable system provides the tools necessary to shield infrastructure against the current tectonic pulse.